computer is working, but this thing is not. All right. So this time my computer is working fine, but the system took a moment. Something has to warm up a little longer. All right, so let's get going. Today we just have a very brief couple of definitions to finalize before we actually start solving problems. So that's going to be definitely more fun. So we have started discussing last time the convective energy. Hi. Do not touch anything, apparently. Convective transport of energy. So just like we had in momentum transport, because our coordinate system is static, right? We just define the coordinate system. We have the freedom to define whichever coordinate system we like, but once we do and settle on a coordinate system, right now the way we are developing equations is that that coordinate system is sitting still, and we know that fluids move around quite a bit. So therefore, we do have to account for the fact that as I'm standing still in the coordinate system, the actual fluid or the matter that I see in a control volume, which is where we develop equations, we always have this notion of a control volume within which something happens, and where I'm averaging or modeling or whatever it is that I'm doing. So essentially, I constantly see different actual fluid, right? So the particles that are passing by are different, which is not always the case, for instance, for solids. If I'm having solid mechanics, typically what I see is pretty much close to what is there all the time, and changes are slight. So there is a definite difference in how we approach that. So but therefore we have to simply, in addition to all of the changes to the energy that could happen within the volume because of the differences in the temperature that actually cause the heat transport, I have to account for simply things literally just moving in with a different energy. So, and we disassociate the two. In reality, it's a difficult thing to disassociate, but mathematically, we actually bin those two things separately. And if we look at the kinetic energy per unit volume, that is 1/2 rho v squared, okay? And also internal energy per unit volume, which is rho u hat, then that's the total energy that moves in. Now, how does it move in? If I have a control volume, I can enter that volume only orthogonally through its sides. So in a Cartesian coordinate system, for instance, the part that enters through the side that is orthogonal, or through the side that is orthogonal to x coordinate vector, is simply this amount of energy that is moving around times the x coordinate of the velocity. It's really v velocity dot the normal to this a little part of the surface that I'm entering through.
With a minus.
With a minus, really done appropriately, but that will actually be, if you just think about the dot product, that's going to be taken by the dot product. And in these equations, we kind of take care of it literally with that minus, but the famous minus. Okay, so, and then of course, then because of that, that's why we say that what goes out through the other side goes out if it's going in the same direction. So, more general formula is simply V dot N. So this is the projection on the normal. Okay, so only things normal to the surface actually enter. Things, all of the tangential components simply slide and never enter the medium, so never change anything inside of that control volume. And ds is my area. So if I were collecting things, I would go and integrate over that surface. Cool. So that is the energy flux vector. Now, we also have to look at the work due to the molecular motion that might change the energy inside. And basically, I know from thermodynamics that the change of internal energy is equal to the heat added to the system, okay, plus any kind of work done on the system. Okay? Or it can be done actually within the system by molecular motion. So my work is force dot displacement vector. Both of these are vectors, so this is where dot product, or this is essentially the reason to define a dot product, if you will. So my work is F dot R, if those are the force and displacement vectors. So if I look at the rate of work, okay, and my force is constant for that time being, then what I will have is that the rate of work, or the rate of energy change due to work, is F dot velocity vector, because my derivative in time passes on only to displacement. Okay? So now I have to translate that to fluid mechanics and my stresses that I actually have. So we know that for molecular stress tensor, we have to look at it separately from convection, right? So we just take the molecular stress tensor that has pressure and shear stress components. So let's look at the work done by those forces effectively. So molecular work flux vector will simply be the stress tensor dot V. Okay. So I will actually have then a combined energy flux which has convective component, work due to molecular forces, and actual heat that is just there because of the differences in temperature. So my simplest cases are those where there are no fluids flowing, or I have just solids. Those kind of easy, right? Then my combined energy flux is simply the flux due to the temperature difference. However, if I have fluids, then I have both of the fluids actually moving something into my control volume, okay? And I have some certain internal friction, right, in between molecular layers, and that creates some heat. Okay. Yes?
Solids also have internal energy, right? Solids also have internal energy.
Yeah, they do. You can't necessarily as easily convert it, but yeah. Accounting the energy conversion is not a simple task. Okay? So now if I actually just write this slightly differently, I can actually write it in form of enthalpy if basically the pressure part of this molecular work flux vector is passed into this energy component. So what happens is that I have, this is my total energy, okay, kinetic plus internal, plus this is PV. This comes from applying identity dot V. Okay? So this is my pressure times volume. That I know that form of work from whatever statics or mechanics class you took. And then I have the work of the shear forces plus Q. So then if I basically if I divide and multiply, but this is 1 over rho, then this actual form is called enthalpy. Okay. So this is just another form to write it down, and this form will be more helpful in actually solving the problem.
What's the big V?
Hmm?
What's the big V?
So this is basically 1 over rho. Okay. So let's now actually do something with that. Okay. So we're going to look into steady state shell balances for heat transport. So this is generally reading is chapter 10. So shell balance, I know what it is. In minus out equals accumulation, right? That's the short of it. Okay. Now a little longer version of it is, a little worthier version, is net rate of energy going in, out by combined energy transport. And when I say combined, I mean convective plus molecular So that is basically what is described by my combined energy flux vector that I have just introduced. Okay? And then I can have work done, so net rate by work done on or by system by molecular transport. Things moving around will create some friction. Plus rate of work by some external forces. So that is typically described by an outside force field working on the entire system, sort of by volume. And plus any rate of energy production. So I might have reactions within my system that some of the byproducts is energy. So when I sum all of those things, at steady state, I'm going to have 0. Otherwise, there's some net accumulation or loss. So before I actually get into solving problems, let's just comment on boundary conditions. Everything is driven by temperature differences, so some of the most common ones is a temperature at a surface, right? So I have some way to keep, if I'm in the lab and I have a core, I have some way, for instance, to keep either the outside energy, I keep things in the oven, outside temperature, I keep things in the oven, or possibly I have a way to actually impose temperature difference from one side to the other. So some of the simplest one is temperature given at a surface. And how you actually keep that temperature constant or at a given value, we leave that to experimentalists in the lab. And here we just assume that it's somehow magically done. Okay. Though that assumption, again, needs always verification. It's either due to some external factors that you cannot keep the temperature source constant and even over the entire surface, or the surface itself might have heterogeneities and different materials. So equilibrating it to a certain temperature might take a moment. Then I could actually have heat flux normal to a surface that is given. And that is basically through surface, right? Now, in terms of what we expect at interfaces of different materials, okay, we typically have some sort of continuity, right? So at fluid-fluid or solid-solid surfaces, we have, so fluid-fluid or fluid-solid interface, solid-solid, I'm sorry. I have temperature continuous, so continuous temperature. And my equivalence of shear stress that we had continuous on interfaces is now heat flux, normal to the interface. So heat flux normal to the surface. So I'm going to just label that as Qn. Now there's a bit of a problem when I have solid and fluids. I know from my introductory chapter, or I hope you remember, that even if you don't remember the actual numbers, that the thermal conductivity of gases and liquids versus solids was order of magnitude or two different. Okay? So that causes trouble in getting some instantaneous equilibration between the surfaces. So I cannot really assume things are continuous at that surface because it takes a moment. Okay? So that is basically more. Yes? Oh, okay. So solid, fluid. Okay. We define normal flux component. And it is Q equal to H, temperature in the solid minus temperature in the fluid. So if I have something like this, right? This is my solid, fluid, and I have certain transfer. So essentially, because of the order of magnitude differences in thermal conductivity, I can support a temperature difference across a solid fluid interface. Or that's a completely realistic situation. And heat is transferred, but it takes, and this is, now H is of course something that we have to have. It's typically tabulated or given by experiments. Okay? So this is called heat transfer coefficient. This is so-called Newton's law of cooling. That is a Q, yes. Part of the quizzes here go to knowledge, and part of the quizzes is like, what did Dr. Kudanovic mean by writing that squiggle?
So you're talking about between solid and fluid interface, there's temperature difference.
Yeah, it's because it's kind of a shock at the interface, right? Because I have thermal conductivity on one side. Let's say that I have a metal. Metal is conductive, right? They would just like to deliver a whole lot of heat flux, but the other side can't receive. That's essentially what it comes down to. So I might be strong here carrying a lot of stuff, but if I'm giving it to a toddler, it ain't gonna happen, okay? So I gotta give it little by little. And it's also going to end up on the floor, whatever you do. This is my experiences every morning. Anyway, so the point is that basically that's why I stay at a different temperature than the neighbor. I don't have ability to equilibrate immediately. It might equilibrate over time, there's no doubt, right? But I can also relatively easily keep it at different temperature as long as the rate of the supply of heat is higher than this transfer to the fluid.
So even in steady state, is it different?
Hmm?
Even in steady state, is it different?
Yeah, you can actually maintain for the time being, again, because of this, if you're getting heat flux from the other side that is heating and you can't transfer for the time being. A steady state is never steady state forever, right? It's steady state in terms of modeling for the time being. So basically, it's steady state with respect to the time scale of the problem, right? Yes.
Don't we use TF for infinite located temperature?
Yeah, it's in the bulk.
Yeah, so it's in the bulk of the other side, but again, you will have a supported difference between the sides. Okay. And again, essential, I'm repeating myself, but essential reason for this is differences in the order of magnitude differences in thermal conductivity. So basically, you can't push through as much heat as you'd like to through all of the system. Mm-hmm.
So in the four components, where does the conductive part come in?
It's inside of the combined. Convective flux, you mean?
No, sorry, conduction. Conduction.
Yes, it's all inside the combined energy flux. That's the one that I defined. Let's solve a problem. But that's basically that combined energy flux that I defined.
Is it Q?
So Q is the one that is there. It's one part of the combined energy flux. Then you have the convective part, right? And the work done in there. Let me go back to that. Okay? Q is only a part of it.
So Q is the conduction, right?
Hmm?
Q is the conduction?
Yes, just by the temperature difference. Okay? So we separate the convective part that is brought into the element and that would be there regardless of the motion of the fluid. Okay. So it's a part of the combined energy flux. So, and we do need to account for that when we solve. All right. Okay. So this is going to be, so I suggest that you chapter 10.2 is a solved problem that you should do on your own. And we are going to do an example that is actually chapter 10.4 in BSL. It is flow between two coaxial cylinders with viscous heat generation. So flow So by coaxial cylinders, we've already solved Couette flow, right, in an annulus. And we're going to use that knowledge part. So let me draw two cylinders, I mean two eggs, the way I draw things. Oops. Kind of eggy. So these are my two cylinders. So this is similar to Couette flow we had before. But there's something that I add, plus I will add heat flux by keeping this temperature at T0. So my inner cylinder plus heat transport due to inner cylinder kept at temperature T0 and outer cylinder kept at TB. Other than that, my inner cylinder is static. And the outer cylinder is moving at a constant speed. And then I do have this, so this is going to be B. So B is my width. Annulus or annular region. So we have already solved this problem for the velocity part, and we're going to use that knowledge. So we had previous solution, and I'm just going to write it down. I had my cylindrical coordinates, so my v theta was the only velocity that is changing. That v theta was different or different with respect to r. Okay, so my only velocity component alive was theta component, and only dimension that this theta depends on was r. So my v theta, and that's simply because of the boundary conditions, because the inner part is at whatever inner radius it's 0, at the outer radius I have a constant velocity. So this is omega r over kappa r minus kappa r over r, or 1 kappa minus kappa. So this was where my B was essentially my r minus kappa r, right? Now we will be interested in the situation where I have very small slit width. And because of that, there is a disproportionate effect of the friction within those layers in the small that can generate heating in addition to what is just their heat flux because of the different temperature. So we're going to assume, I'm going to change color again, assume B is much, much smaller than radius. So I can neglect the curvature of the system and I kind of zoom in. It's like, how good are my glasses, right? Somebody was discussing contact technologies before. Same situation. So now when I zoom in and my B is much smaller than R, what I'm gonna see is flat surface, just like on this Earth. We're thinking, and there are still some people thinking it's flat. Okay? In 2018. Satellite images, no, notwithstanding. So anyway, so basically when you zoom in locally, you think it's flat. So that's what we're gonna do here. So we can ignore curvature in order to simplify the system. So basically when I zoom in, this is what I see. And I have my sort of velocity profile locally. Looks like I have a little slit, right? So I'm gonna call this actually my Z, and this is going to be my X. So I'm gonna introduce new local coordinate system. And this is going to be my Vz of X. So my V theta of R has become Vz of X in this. So this R in kappa RR, my math background is peeking through this symbol here, element of, becomes X in 0B. Right? And I can also linearize this velocity profile locally. So my Vz of X is simply omega R X divided by B. So it's 0 at 0 and omega R at the boundary, right? So just linearized version of the above solution. And if you take proper limits, you can actually get that for the small, basically for kappa close to 1, right? You can get this linearized profile. Okay. So now we have this, we have the velocity as given. We're going to just use this solution. Okay? And we have this temperature difference between the fluid. But there is also this extra friction part. I have very small slits, so basically the viscous heating is somewhat disproportionate because layers are very close and these surfaces are really close. So essentially there will be, instead of what I would expect as a flat or this linear temperature profile, it's not going to be linear. There will be addition due to heat generation within the system, and I'm just wondering how big is that. That's pretty much it. Otherwise, if I just had a slit and there was nobody moving, I know that my temperature profile is simple, linear function. Right? So I'm just wondering, well, okay, what is the difference, and is that difference becoming significant? So we want to figure out is that temperature differences due to heat generation. How far am I from linear T profile? So let's compute shell balances. My assignment for the next time I teach this is investment in a software that would, like in Khan Academy, just have a continuous surface. But the reason why I do this in pages is that I can export proper pages, so the software doesn't have to figure out where to break as I'm writing things down. Because that's what becomes the problem when you just have a continuous sheet, breaking it down in actual pages when you're producing notes is a problem. But it'd be nice instead of this opening, closing, opening, closing, opening, closing. All right, so my shell balance is done over a simple Cartesian coordinate system. Okay. So I have my x and x plus delta x, and my z and z plus delta z. Stuff coming in, stuff coming out, stuff coming in, stuff coming in and out. This stuff, what is the vector I describe it with? So I have my E is combined energy flux. Which component of it will actually be entering through this side at x boundary? Ex. And also exiting on the other side, and here Ez. Yes. So we don't have external forces or any kind of generation within the volume other than that from the friction and the work of the molecular forces. So that's that's not a source in itself, right? There are no other sources. So basically, net rate of E, basically E in and out is equal to 0 is my shell balance. And this is it's EX. It technically has a Y component that we're ignoring, right? So balance, something awfully simple. EX times the length of this, right? Minus the other side. And that's the part for just this x component, I do have to add the z part to it, right, as well. So essentially, I will have, since I also have to look at this that, yes, I zoomed in, okay, but I am still part of something that is constantly moving around in a coaxial cylinder. So actually what's coming in and out of Z, the net has to be 0, right? So both the X component and Z component, they have to be 0 separately, right? Because otherwise I would have like generation in a circle. So that could be fun. It's called perpetuum mobile, right? Of some sort for heat generation. So what I'm going to have is that essentially is my EX balance says that EX at X times the length of this side is delta Z and some sort of length in Y direction. I'm just going to call it LY. I'm going to divide by it anyway. Minus EX evaluated at X plus delta X delta Z LY has to be 0. And I divide by volume of the element and delta X. And I'm going to have that minus EX XX plus delta X over delta X is equal to 0, which of course I take the limit of. And what this comes down to is that the partial derivative with respect to X has to be equal to 0. That's as simple to integrate as it gets. So my X, EX is simply some constant. However, to solve it, I don't have boundary conditions on energy, or rarely, or combined flux. Right? So I gotta break this down. My E is 1/2 rho V plus rho H V plus tau dot V plus Q. So that is my combined energy flux vector. If you remember, we combined the pressure part of the molecular forces we combined here with internal energy into enthalpy. So what is the EX component? Plus rho H Vx plus tau dot V X component plus QX. What is Vx? Yay! Because of Vx. That's happiness right there. I don't have to figure out enthalpy or anything like that. We will in further examples, but for right now we're safe. Okay. Now this is a tensor dot vector, so that is actually I can choose blue. So this is tau xx vx plus tau xy vy plus tau xz vz. So that's the x component. Yes.
Is that rho V, half rho V, is that also an x component? The V inside?
No, v. This is v squared. Is this one?
Yeah.
Yeah, that's v squared. That's just the absolute value. That's a scalar in itself. So that's just the kinetic energy that I'm carrying. Okay? And in itself is a scalar value. So no, you don't take, that's just v squared. So v squared, it's a good point, I never. So this is Vx squared plus Vy squared plus Vz squared. And again, it's the energy that is carried with the fluid. So. And it's scalar. Now this is x component. This is basically matrix dot v, matrix vector multiplication really. And you just take the x component of it. Now, some of these parts are 0 as well. So this is 0. This is 0. Okay. So I have this component that is not. So my Ex is actually equal to minus mu dVz dx times Vz plus Qx. What is Qx? Minus K d T. That is my Ex. And that is equal to constant. So just to see where we go in 1 second. The partial differential equation for the energy itself is going to be deceptively simple. However, that's not what we can measure. We measure temperature, okay? And we're looking for temperature distributions. So I got to break it down. And then I have to look at all of the components. Ultimately, what I'm looking for is this temperature, right? So this is where I can actually get my temperature from, if I know Vz. But if not, it's coupled. Okay? So all of these problems, we will kind of freeze my velocity distribution that I know from the initial portion of the course. And then I'm going to use it, right, to actually recover what dT dx is, or what my temperature distribution is. So in this case, it's going to be relatively simple. We linearize this profile, right? So this is not going to be difficult to solve at all. Right? But that's essentially what we're going for. Okay? And we're going to have, in this case, this is going to be a done problem because the only differences in temperature I expect are in this x direction. I don't expect them in the z or coaxial, like what was kind of running around the annulus direction. So this is going to be it by the time we solve this part. The other parts, we can look at them, but they're not going to give me any extra information. All right? See you on Friday.
Dr. Mata?
Yes.
Could you download the math microscopy balance